شكرا على الدعوة الكريمة. معكم Khaled Goher. I'm associate professor now with the University of Nottingham. I'm currently the academic research lead for open source assistive devices laboratory. This is based at the Faculty of Engineering, University of Nottingham. I have like some admin roles as well in terms of deputy director for the mechanical engineering program. So it's my pleasure to present my slides here, which will be a brief about engineering innovation for assisted living and the importance of technology transformation. Just before I start talking about the details of my research and why I selected this particular topic for my talk, I just believe in like having a cross-disciplinary research. And when we are talking about assistive devices or assistive technologies or biomedical engineering, I can't see this research field other than being cross-disciplinary. I put here like a slide which I just try to adapt in all or most of my research at these days over the last 15 years. So the stakeholders and end users are on the core of this research: engineering, computer science, clinical science, social science, physiotherapy, and biomechanics. But this research will need non-government organization to be involved. Industry is a key part, public sector. And the reason to have all these stakeholders in this particular cross-disciplinary research, because working on assistive devices, biomedical engineering, or healthcare technology in general has a social impact. That's why it is very important to have a multidisciplinary team working in this research. This is like a brief outline of my talk today over the next 30 minutes or 40 minutes or so. So I will why assistive technologies or innovation assistive technology is very important. I will talk about some research significance here. And I selected a number of areas to be the focus of my research, and I will give some not a detailed information about how 3D printing is used in assistive technologies, but I will give a brief why 3D printing is very important and their role in innovation in healthcare technology. Before I introduce 3 of my research projects, which comes in step number 5 here, I will talk about the challenges facing research in children prosthetics, and this is an area which I'm focusing on now for the last around 5 to 7 years. Finally, I will give a brief reflection for the future, how I see this research is developing and where it is going to, and what are the main drivers for this research in the near future. Just some numbers here. Rational, you can consider it as rational, or like figures, justification, why I'm focusing on this research over years and years now. Assistive technologies like not a secret, as the population of the whole world is aging now, and mainly in the developed countries. The majority of the population are aging population, and this justifies why we need to have work and more focus on customized assistive technologies for people who are in real need. I have like 3 slides here, just talking about numbers, figures. I know like we are not focusing too much on like what is the market needs, etc. But I feel this is very important to justify why there is an emergent need for more assistive technology research, more targeted assistive technology, and customization design for people who are in real need for innovation in assistive devices. And when we look at the 3 drivers for this particular field, the increasing incidence in trauma and accident injuries, especially in areas of conflict, wars, etc., or many accidents due to different reasons or different types of diseases, like the diabetes is one of the main regions in the developed countries. The second driver here is the introduction of custom-made implant product. This is another area which is as a main driver. And the favorable reimbursement of orthopedic prosthetics is another thing which is like as one of the main drivers in orthopedic prosthetic market. I just put here some data for the 7 years between 2018 and 2015. Before I start my research, or before I start my talking about the details here, this is about the market opportunities for 7 years between 2018 and 2025 for the upper limb prosthetics. And I'll give you a moment here to reflect on the numbers, how huge the market is. And if you look at the market share, for example, for the prosthetic devices sector, this is around 30% now. Vascular diseases, diabetic sectors like 54, nearly 54. Terminal devices, hospital segments are like taking a big share as well. So like when you look at prosthetic devices, which is my current focus now, this is a huge share in the market, and this is justify why we need to focus on this in our research. The smart healthcare market even is not my current focus at this stage, but this is like a huge future for it coming, and I think we just need to be ready. And I will reflect in my last slide on why artificial intelligence and machine learning are very important in healthcare innovation. I'm just approaching now like the point where I will start to talk about my research and these topics which I put here as under this title for innovation in healthcare. Again, I'm really driven by numbers and the significance, the need of people, the needs of the society, either here in the UK or elsewhere in the world. This is some random statistics here, which is like everyone, we can get it like from the internet in a minute. And just you probably will be shocked by seeing the number of disabilities in Africa only. As I mentioned before I start here, this is like random selection. So I'm not focusing on any particular region. This is randomly from different regions of the world. Even Africa has 80 million people with disabilities. Of course, with different types of disabilities, many of them with mobility disability due to conflict or whatever. Even the United States itself is like around 185 amputations. This has happened every year. And by the way, this data is around 2020, so around 2 or 3 years ago. Around 25,000 people upper limb amputations happen every year. But one of the major issues we will face, and this is one of the main drivers for my research group, is the rejection rate among people to use prosthetic devices is very high. So many people have amputations, but many of them, they reject to use prosthetics for different reasons, and I will talk about this in details in one of my projects. Complaints about discomfort, lack of utility, weight of a device, or mainly for general assistive devices or prosthetic devices, is one of the major barriers for people to use assistive devices in general. Just focusing more like now on my region where I live now is, just believe it or not, like around 7,000 amputations every year in the UK, with around 135 legs every week. This is like something huge, by the way, to happen. The National Health Service, for example, is like spending too much, nearly 60 millions around 2 years ago, around 60 millions only for limb deformities. So these statistics here can give you a feeling of why we need to focus either locally or regionally or worldwide on assistive devices and bring innovation solution to resolve issues for many, many peoples in our society. My second part of my presentation, because I'm adapting 3D printing a lot in my research over the last probably 7 to 10 years now. So before I start introducing my project, I will just talk very briefly on the role and the importance of 3D printing in innovation and healthcare technology. This is like some information about the current spectrum of technologies in 3D printing. different technologies with different complications. Eyes range from cheap material, cheap machines, simple technology to more sophisticated technology. So extrusion of material jetting, VAT polymerization or SLA, like polyjet, fusion deposition, material, etc. But just before we proceed more on 3D printing, because I focus more on soft robotics over the last few years, and I adapted soft robotics a lot in my research. So relying on using soft material becomes a very important and core part of my research and many other research groups now everywhere. And the reason for adapting soft robotics material because they are compatible, they are more comfortable, less weight, etc. And when you look at this table here, the different hardness of this soft material is a very important factor, because and this will decide on the material selection, the type based on the type of product, requirement of a device, applications, features, functions, etc. Examples here of the fusion deposition modeling. This is like examples of soft actuators, of soft devices which can be used for assistive technologies. And fusion deposition modeling, or FDM, is a cheap, accessible type of technology. We suggested it for beginners. Commonly used because it's rapid prototyping technology due to the ease of access. It falls under material extrusion. But we use filament, which is very cheap, around $25, for example, for 1 kilo of filament, or cheaper, depends on the type of material in way. So as a starting point or a starting technology for 3D printing for innovation in assistive technology, we suggested to start FDM, or fusion deposition modeling. Stereolithography is more expensive type of technology. SLA was VAT photopolymerization, or optical fabrication. Photosolidification is resin printing. These are all different names for the same technology, SLA. More expensive to run, expensive machines. The resin itself is more expensive, so probably 1 liter of resin around between 150 pound to 250 British pound. More expensive to run, but will give you more flexibility in terms of 3D printing of different types of material, ranging from resin to resin, soft materials. Material jetting, or polyjet, is another more advanced type of 3D printing. Is used a lot now in innovation for healthcare. Very similar to the printing, but just with each printed layer stacking up to form the 3D part. But the main feature of this type of printing, you can print in different colors. You can print in different materials as well. And when you think about prosthetic devices or assistive technologies, exoskeletons, wearable devices for people, having feature of printing of different type of materials, different colors, is sometimes required as well. SLS, or selective laser sintering, it's another type of additive manufacturing, and this uses a laser as a main power and heat source to sinter powdered material. And sometimes we use nylon or polyamide. But again, this is another type of expensive type of 3D printing, additive manufacturing technique, commonly used now in innovation for assistive living. Over the next few slides, I will introduce different types of products by different types of 3D printed printing technologies like FDA. So from the left here, like you'll find different types of actuators for different applications, like soft robotic elbow sleeve, for example, here. Single channel actuator, multiple channel actuators. Some of them are giving linear actuation. Others can give a twist motion, which is needed, for example, for knee rehabilitation or following knee replacement operation and so on. This is like a table, give like a recent summary of how fusion deposition modeling have been used in 3D printed printing in healthcare for different application from different groups worldwide. PolyJet, again, as I mentioned before, like more advanced, more expensive to run, color feature printing, multiple layer printing, etc. is another. These are different types of actuators by PolyJet technique. SLA, and I'm using this a lot in my research over the last 5 years by developing soft rigid actuators, and I will give a detailed example of one of my research projects later on my presentation on this. A final summary here of different types of pneumatic soft actuators design, either like extension, contraction from the top left corner here. Some soft actuators which provide bending features, which is from the second row here, number one from the second, twisting or helical type of actuators, bidirectional, omnidirectionals. All these type of soft actuators, they generated a huge spectrum, huge opportunities for development in healthcare these days. Right, just two more slides before I talk about three more of my research here. I will start, I mentioned at the beginning here, on focusing on children prosthetics. The challenges for children prosthetics is affordability, and mainly if we are talking about the developing nations. Not necessarily the device need to be complicated, but at least need to be customized to provide the necessary function for the amputee. Early exposure and adoption of prostheses for children. Statistics research show that unless a device is adapted or used by a child before 2 or 3 years old, the rejection rate will be very, very high. And why I mentioned about 38% of is a rejection rate currently. Modularity in designs is another field which is a recent focus now of many research groups around the world. And mainly when we talk about the children, I just put here a brief message. They grow, and prosthetic devices as a customized assistive technology device is not growing with them. That's why just you need to think about like replacement every maybe other year or whatever, or like maybe every few months if at an early stage. And this is a huge impact, financial impact on health authorities or families or people who are supporting a particular child who has a problem with like an amputation. Again, this is following on there's the same thing, importance of early fitting of active prosthetics in reducing rejection rate. There's too many research happening now in different research groups, and I brought here one example. Children who don't use prosthetic devices often develop issues surrounding posture and musculoskeletal pain. This is a recent study, not that recent, just 5-7 years ago, I think now. There is a huge potential now for wire-driven soft grippers to be used in assistive devices and mainly for healthcare technology for prosthetics mainly. Like just very brief information, fundamental information on the type of amputation, either upper or lower limb. I focused on both on my journey over the last few years, and I will mention about my first project here is transdermal amputation, above knee amputation for a child around 2 years old, and we developed the first myoelectric device, a prosthetic device, and this will be the first project to introduce to you guys. Right, I will just put numbers here, 1, 2, 3. This is project 1, the soft grasp infant prosthetic arm. We call it SIMBA, and mainly here just we target a particular age group less than 2 years old, and it's a huge challenge. And mainly the reason here for the drive for us to start this research, because the National Health Service NHS in England is not providing any prosthetic devices for any amputees children below than less than 2 years old. And the reason for this is very well known because of the financial implication, because if they can provide a child with, this will be like few £1,000 for a basic device. So we believe we managed to produce or to develop a device for this age group, which was a big challenge for us. Right, it's like this was a master project research, and following now by another phase of a more advanced research, usually by a PhD student. So mainly is the end device here utilize wire-driven soft grippers, as you can see from the pictures here, which has been, and the 3D printing has been used here mainly by two types of different 3D printing technology, FDM, fusion position modeling, and SL is a stereolithography. Of course, here we did some kinematic analysis for the device, but again, this is a huge approximation. This is not a rigid component, but this has been approximated as a 3-arm link. That's why you can see this very traditional kinematic equations. But again, this is a huge assumption because we are dealing with a soft material, not rigid links. The grippers are composite, manufactured out of 2 different silicon rubbers. And I bought this particular graph here, like to show, like, give you a feeling of when you use a soft gripper or a rigid gripper, and the conformity with the contact surfaces, what we are looking for when we think about soft grippers for assistive devices or for prosthetics mainly. It's a myoelectric device anyway, because mainly the electric signals is measured from the muscles. We record it and we control the system using surface electromyography. We did a lot of testing in terms of the grasp force testing, the pinch test procedures. We used different types of weights, different types of objects, different types of shapes to assess and evaluate the success of this project. So this is like a nice study using different types of daily used objects like keys, pen, different toys, a bottle, different types of geometric shapes like a cube, etc., cylindrical shape, etc. And the reason we selected these here, because we did a study on what are the common activities a child under 2 years old is doing, mainly like draw something or try to start using a pen to draw, or holding a toy, or holding a bottle of water or milk. And we assess the project, and we had like some really good statistics here on the success rate based on different configuration of objects to be grasped. Again here, like this is like mainly just assessing about how successful the grasping of a particular infant prosthetic arm has been done. This has been published in IEEE Robotics and Automation Letter, and ICRA, IEEE Conference for Robotics as well. The second project here is rigid actuator for assistive technologies. So away from the traditional research or using rigid actuators or rigid motors, this is not going now too much with assistive devices. So people now, like research groups now, are moving toward more of use of soft actuators. What we believe in is just having a hybrid combination of soft and rigid material for soft actuators can provide high power. For example, when you think about exoskeleton devices, this is another field here which needs a huge power, and that's why the reason we are thinking about hybrid combination of soft and rigid actuators. This is like some data here, some literature of soft wearable robot design and characteristics, and we mentioned here about 3 different well-known ones: elastomers and magpine, textile, and fabrics here with advantage and disadvantage for each one. And when you think about this picture, like all this has been designed and developed later on by 3D printing technologies. Exoskeletons is for knee assistance. This is one of my current research now for 5 years. I have like a number of students working on this one as well, by developing soft rigid actuators for exoskeleton and mainly for knee assistance. This is like part of the literature we did, and because we wanted to understand what is going on now with different research groups, and we identified the system weight is one of the challenges here, and that's why we are moving more toward lighter actuators, but more powerful actuators. And this is the main challenge, because soft actuators at the moment they don't provide enough power. That's why we wanted to focus more on a hybrid approach by soft rigid actuators, with the hope to make it a light actuator, compatible with comfortable and compatible with the human body, and can produce enough power to support, for example, a whole body weight during different daily activities. This is again like the comparison between different approaches by the muscle effort reduction based on different approaches. One of the challenges here is most of these will be pneumatically powered, which means that you need to have a pneumatic source, which is again an extra weight for the device. So we focus on this project here on different work packages. One of them is a soft valve and a soft rigid actuator, and a system integration for knee assistive devices. We start already as a first package now, which I will introduce in this research. Marine, before I elaborate more on the details of this research here, one of the things which we are looking at is output force, how we can maximize the output force from a soft actuator. We are dealing with the soft actuator speed as well, because they are generally lower speed compared to rigid actuators. So we try to maximize the speed of response from soft actuators in order to just give a similar response or like response to the speed of a rigid actuator. Power consumption is something it's looking at in this research. And of course, the device weight. This is like the soft rigid actuator, as I mentioned, we are currently working on. So like we finished the first work package. So it's mainly a combination of features of soft materials and rigid combination of different gear systems, etc. And we hope this one has probably give us like better opportunity for a higher power, but while we have less weight. So mainly like this is a 3D printed valve, soft rigid valve here to control a pneumatic artificial muscle. The valve can provide high flow rate, and we proved that it can provide high flow rate comparable to other rigid valves in the market now. The 3D printed artificial muscle is used to validate. We are using artificial muscle to validate controllability of the valve. We did number of testing here for understanding the characteristics of the device by different pneumatic circuit arrangement by different types of muscles. And this is what, for example, here like shows a dynamic response and the flow rate which we can achieve from this particular valve. Again, like we wanted to understand more about the flow rate here, and based on the opening orifice of the valve here, so we did a lot of research on different types of like different diameter of the opening of the valve and how this will affect the flow rate, because we were looking for like a particular flow rate for our particular application. Another like just small grace muscle here using our valve or pneumatic kit, which we provided in our lab between University of Lincoln and the University of Nottingham, which I'm currently working for. So we use like this tool, a 3D printed grace muscle to validate the performance. This is the grace artificial muscle, a 3D printed muscle, which we produced ourselves. That can contract and elongate using pneumatic controllers. A fabricated muscle is a contraction model in a way, which can reach contraction ratio around 25% when it is pressurized by around 26 kilopascal. And it is made of ATA is a flexible resin. We used it for stereolithography. So this is mainly has been produced by SLA 3D printing using ATA flexible material with 40 millimeter height. The third with it is like a chain of 5 grace muscles. It's another test to validate the valve here. The mechanism is used to validate a valve ability to control the high volume actuator with required frequencies. The mechanism was connected to a chain of 5 grace muscles to reach the required angle 60 degrees, which is the maximum flexible flexion of any joint during the walking motion. Again, like our target here is to develop a soft rigid actuator for knee rehabilitation. So we are moving steadily, slowly but steadily toward achieving this here, using a soft actuator rather than a rigid actuator. Finally, we did a comparison based on our research and the sonic conductance for our actuator and other available soft valves in the market as well, and we achieved this by a good success.
Can you go a little bit faster, please?
Oh yeah, sure. Just yeah, sure. Finally, this is like the last project here. This is structural optimization of adaptive soft and fin ray fingers. Just like when you look at the fin ray fissure, actually what happened here, the stiffness capability can change. So we developed here a grabber for assistive technologies for prosthetic devices, mainly based on the fin ray design. So mainly if you look at the object here, when you push this object toward the fin ray on the right side here, the ribs will get closer to each other. So the stiffness initially will be different from the final stiffness. So we did a lot of optimization here in order to maximize the type of stiffness we can use based on the different types of grasping and so on. And if you look at this particular example here of the soft grip on the left top corner, this is how the soft gripper changes the stiffness capability based on when it started to interact with a particular object. So we did a test in our lab, and this is like how you can see the ribs when they get closer to each other will change the stiffness, and having different or variable stiffness capability. This will give you a huge opportunity for different applications, because when you think about exoskeletons, for example, sometimes you need extra support or full support. Sometimes you don't need any support, for example, for the exoskeleton. So we need to have a capability or variable stiffness capability for based on the different feature, different application, different modes of operation of a particular device. We did like part of our research, we wanted to know about the resultant force from the jamming. Jamming is when the ribs get closer to each other, and what will happen to the finger displacement of the tip point of the finger itself, because this will allow us to understand more about the interaction between the object and the grip. This is like my last slide. I'm sorry to taking too much time anyway. This is, I can see 3D printing and the 3D scanning has a huge potential for prosthetics or assistive technologies in general. Machine learning, artificial intelligence, this is something we focus now on, how this can be implemented for enhancing the field of research in assistive technology. Modeling of soft robotics is still very early. There's too much research can be done here, and we just only started to understand a bit about the modeling of soft robotics. Thanks for their attention, and thanks for the invite again.
Thank you very much, and you are welcome. And we'd like to see you sometime here, next conference here in Syria. Thank you.
Thank you. Thank you.